Hi there and welcome to this video for Senior Physics on Electrostatics and Electricity. In this video we're going to explore the basic concept of resistance. There will be other videos which will look at internal resistance and also what happens to resistance in a series and parallel electrical circuit. Now, resistance was first explored by Georg Simon Ohm at 1787-1854. And basically what he did was he looked at the effect that different objects had with respect to how well they actually allowed current to flow. And from this, he used a simple equation, as you can see here. He used a battery. He then linked that battery via an ammeter to a resistor, and then he looked at the voltage that was spread across the two sides of the resistor. He looked basically at the amount of energy that the resistor put up to the current. And as a result, by changing the battery, he was able to then affect the ammeter, and then as a result, he tried to come up with a relationship between V and I. And from this, he got a relationship which we call an ohmic relationship, which was a straight line, which basically means that V is proportional to I. And there is a constant from the gradient of that line. That constant happens to be the resistance of the actual material. Now, obviously, as the material is not going to change, the resistance, one would think, is going to remain constant. However, there are slight problems, and this comes up in non-ohmic conductors, where what tends to happen is you get a graph which is similar to this, or it can be the reverse of this, so it's actually going in an exponential shape. And what this basically means is that the resistance is going to change due to a change in current. Now, the reason why this is because if you put more current into a material, you actually increase the amount of resistance, you increase the amount of heat. Heat causes the material to expand. That expansion means there's more space. More space means there's less resistance, which means that the result is that it curves off. Now, most materials are non-ohmic, but at certain temperatures, they will be ohmic and obey Ohm's law. So, Ohm's law can principally be stated as the current flowing through a conductor is directly proportional to the potential difference or the voltage which is applied across the ends of that resistor as long as the temperature and all physical conditions remain constant. Now, from this, we get an algorithm. Now, the symbol for resistance is given R, and the units is ohms, and the symbol for ohms is omega, as we can see here. Now, placing his findings together, we get V is proportional to I, and there's a constant in the middle. Well, that constant happens to be R. So from this, we get V equals I, the current, times R, where R is the resistance, the constant, which happens inside the actual material. Now, V is measured in volts, resistance is measured in ohms, and current is measured in amps. Now, as I stated, resistance occurs in all conductors. If we had a very, very good conductor, for example, a copper wire, the result is that we would have very small resistance, which means that we would not lose as much energy as it passes through. Now, one way that I've described resistance is the idea of running something like a gauntlet or trying to run through a crowd. Now, if you were trying to run through a crowd and all the crowd was made up of was something like little kids, then you'd be able to run through that crowd no problem as an adult. Now, let's say you then take that same crowd, but instead of having little kids, you've got large adults. Now, to run through that same crowd, but with large adults, you are going to expend a huge amount of energy pushing them out. Now, imagine that you happen to be the charge. Your voltage will be the amount of energy that you've got in your system. As you move through the particles of the conductor, the crowd, the result is you are going to expend huge amounts of energy. In the kiddie crowd, you're not. There's not going to be a lot of energy because the kids can be easily moved. Well, remember, the kids or the adults in the crowd are your atoms inside the actual conductor. So think about it. In a high resistance scenario, you're going to be trying to push your way through a crowd of very, very big adults. And the more adults you've got compacted in there. The more resistance there is, the more energy you're going to give out. With small children, you're not going to have too many problems. You can pack it full with small children, you can still push them out the way, and the result is that you won't expend much energy. Word of warning, don't ever do this in reality, otherwise you could get yourself in a lot of trouble. But hopefully the scenario sort of gives you an overview as to how it works. So the current in a conductor depends on the resistance and the voltage which is applied across it. And that's what Ohm's law states. Now, resistance can often be very large and often is given in the terms of kilo ohms or mega ohms. Now, there are a variety of factors which can affect the resistance. One, obviously, is the material and the type of material that we're dealing with. But there are two other things, especially when we're talking about wires in an electrical circuit, and they happen to be length and gauge. Now, for length, we get the scenario that if we decrease the length, we decrease the resistance. Now, what that means is, if you've got a wire of a certain amount, okay, let's say it's a crowd of adults again. Let's say we've got a crowd of adults, but we only make that crowd of adults very, very small. There's only a few atoms in our way. Then we are not going to expend much energy going through that crowd of adults. But what happens if we get a longer line of adults? Well, this is like the same as increasing the length of the wire. By increasing the length of the wire, I've got a longer amount of adults, which means that I'm now going to be expending a lot more energy. Now, where do we see this in practice? Well, an old heating element, or any heating element that you might have in, let's say, a hairdryer. Inside a hairdryer, you've got a long coil of wire. That wire has the same scenario, having a large amount of adults that the current's got to pass through. As it passes each adult, remember the adults are basically the atoms, it gives up a certain amount of energy. Well, collectively, as we go through a long line of adults, we're going to collectively get a huge amount of energy expended. That's why the wire glows. We have to get it to a point where the wire just glows. Otherwise, if it gets too hot, the result is it melts. And also the resistance will actually begin to decrease if it gets too hot, simply because what happens is the integrity of the atoms changes. We go from ohmic to non-ohmic. So if we decrease the length, we decrease the resistance. If we increase the length, we increase the resistance for the same material and the same thickness. Now, I mentioned that word thickness. Now, another name for thickness with respect to wire is called the gauge. Now, in a scenario, we can have thick wire or we can have thin wire. Now, thick wire basically has the effect of having an increased gauge. If I increase the gauge, I decrease the resistance. Well, what this means is it's like having the same number of adults, but I spread them out over a larger area. The result is I can get more current flowing through. So instead of having like two sets of adults that I can go through, I might have 4, 6, 8, 10, and all my current can be flowing through those various channels, working on the idea that metals basically have a nice structure where we've got channels. So if you increase the gauge, we can increase the number of channels through which the electrons can flow, and as a result, we can get more electrons through per second. That means we increase the resistance. We increase the current. Okay, increasing the current will result in decreasing the resistance, which gives us the same voltage. Okay, now the opposite of this is decreasing the gauge. If I decrease the gauge, there's less channels for the current to flow through. As a result, we're going to increase the resistance. There's going to be a build-up. So if you imagine not just one electron running through our adults, you've got like hundreds of electrons. If you've only got one channel, you'll get a backlog. If you've got 50 channels, then the result is you can get 50 electrons going through per second. Okay, as a result, we basically increase that resistance, increase that current, we decrease the resistance, it gives us the same voltage. So I hope that makes sense with respect to resistance. If you join me again for the next few videos in this post, and we will look at the effects of internal resistance and how we basically determine series and parallel or resistors in series and parallel. Well, thank you for joining me, and I look forward to meeting you again. Bye for now.